Okay, let's start with our lecture. We were discussing in our last class about the Bernoulli's equation along a streamline. So what we developed was that Bernoulli equation is basically an equation which is used for fluid flows, but with 3 or 4 conditions. The first condition is that Bernoulli equation can be applied only along a streamline. So you have a fluid flow, fluid is moving from one point to another point, and Bernoulli equation can be applied at any point within the fluid flow if it is along the streamline. So this is the first condition. The second condition is about the fluid itself. The fluid should be incompressible. Incompressible means mostly liquids, because the gases are considered compressible. So this Bernoulli equation cannot be applied directly over the gases. The third thing is that the fluid flow should be steady. So if the fluid flow is steady, is not varying with time, then we can apply Bernoulli's equation over the fluid flow. And the fourth thing is that it should be inviscid flow. Inviscid flow means viscous effects should not be there. Viscous effects should not be there means it should not be anywhere near the boundary layer region where you have a fixed boundary of a fixed support. So there are regions where there will be relative motion between the layers of the fluid. So whenever you have the relative motion between the layers of the fluid, so the viscous effects are applicable and the flow does not remain inviscid. So for the flow to remain inviscid, it should be away from the viscous effects. Okay. So if these 4 conditions are satisfied, then Bernoulli equation can be applied. Okay. Now, what does the Bernoulli equation says? We discussed this, we proved it last time. The Bernoulli equation says that summation of 3 different kind of pressures are constant. Okay. So we have the hydrostatic pressure, P, plus we have gamma Z, which is the pressure due to elevation. And then we have rho v square upon 2, which we either say as dynamic pressure or we say kinetic pressure. So the pressure due to the motion of the fluid itself. So combination of these 3 pressures will be a constant along any streamline if we have if we apply the Bernoulli equation over the fluid where the conditions for the Bernoulli's equations are validated. So we have these 3 pressures, or in terms of the heads, we can write it as hydrostatic head plus elevation head plus kinetic head or dynamic head. So summation of all these 3 heads will be a constant along a streamline. So this is Bernoulli equation. As we already discussed that hydrostatic head plus elevation head, it is termed as piezometric head. So we can also say that piezometric head plus velocity head or kinetic head or dynamic head, these are the 3 names for the same term. Okay, so these will be constant. So this was the Bernoulli's equation that we discussed last time. We also showed it over the Venturi meter. This is the Venturi meter. So Venturi meter is just when you apply a restriction in a pipe by constricting the diameter of a pipe to a smaller diameter and then returning it back to the original diameter. So this, because of this constriction, we call it, this is the throat region. Okay, because of this throat region, we have a kind of a construction here, which is known as Venturi meter. Okay, this is a construction which is specifically used to measure flow. Sometimes we can also measure the pressures. Okay, and also through certain means, we can also find out the velocity of the fluid, but just by applying this restriction in the flow in the form of a throat. And this is known as Venturi meter. So we have also shown there on the Venturi meter that how is the Bernoulli equation applied? The Bernoulli equation says that the total head is constant. Now, total head is composed of the kinetic head, then it will have the hydrostatic head, and then it will have the elevation head. Okay, so sometimes the elevation head increase. So in that case, if the kinetic head is also increasing, then the hydrostatic head adjusts itself such that their summation remains constant. So in the same way, even if the flow proceeds further, okay, with the Bernoulli equation being satisfied, then still the summation of all three heads, elevation head and hydrostatic head and kinetic head, summation of all them remains constant. So this was just an explanation done over a Venturi meter, and this is still what we did in the last class. Now we're going to apply this knowledge on a numerical here today. So let's see this problem statement. So we have piezometric tubes are tapped into a Venturi section as shown in the figure. Okay, the liquid is incompressible, so that means it's a liquid which is flowing through the Venturi meter. The upstream piezometric head. Now, first of all, do you have an idea of what is the difference between upstream and downstream? So this comes from the basic understanding that water flows top to bottom. Okay, so when most of the time when the water is coming from the hillside, so from the top the water is going down. Okay, so top is considered as upstream, and then bottom would be considered as downstream. But now you have to understand that here upstream and downstream does not necessarily means up and down. What I have explained you is how these terms emerged. Okay, so upstream, because water normally used to come from the hillside, so hill was already in the upper region at the upper elevation. So water is coming from the up elevation to the down elevation. So at the upside, it was considered as upstream, downside was considered as downstream. But now these terminologies have evolved, and now what upstream means earlier in the flow. Suppose if the fluid is moving from down to up, then the upstream will be the downside and the downstream will be the upside. Okay, so earlier in the fluid motion, that is the upstream. Later on in the fluid motion, that is the downstream. Okay, so fluid is moving like this. Okay, this is the fluid direction. So this will be the upstream, this will be the downstream. Wherever the fluid is starting or the earlier in the fluid motion, that is the upstream. Wherever the fluid is ending or the later in the fluid motion is the downstream. So it does not necessarily means higher elevation, lower elevation. No. Yeah, it emerged initially like that, but later on now, whenever you have a flow, so you have an earlier part of the flow, you'll have a later part of the flow. So earlier part of the flow is an upstream, later part of the flow is a downstream. Okay. So it's just a simple explanation of the upstream and downstream. Okay, so the upstream piezometric head. Upstream piezometric head means this is a Venturi, and it is shown that the fluid is flowing like this. So the piezometric head here, earlier in the flow, upstream. Okay, so the upstream piezometric head is 1 meter, and at the throat would then be the downstream because the fluid is moving in this direction. Okay. So here, the upstream piezometric head is 1 meter, and the piezometric head at the throat is 0.5 meter. Okay. The velocity in the throat section is twice as large as in the approach section. So approach section means from where the fluid is approaching. The fluid is approaching from this end. So the upstream section is also considered as the approach section. And then this is the downstream section or the throat section. Okay. So velocity in the throat is twice as large as in the approach section. Find the velocity in the throat section. Okay. So here, now this is, if we consider this as an inviscid flow, suppose if we consider this as an inviscid flow, then for the inviscid flow, it is a steady state, it is incompressible because it was mentioned in the question that the liquid is incompressible. And if we are considering along the streamline, then a Bernoulli's equation can be applied. Now I can apply the Bernoulli equation at point 1, and I can apply the Bernoulli equation at point 2. Okay, at point 1 and point 2, I can apply the Bernoulli equation. So if I apply the Bernoulli equation between point 1 and point 2, so my Bernoulli equation will be like this. So it will be P1 upon gamma plus Z1 plus V1 square upon 2G equals to P2 upon, sorry, P2 upon gamma plus Z2 plus V2 square upon 2G, right? So this will be my Bernoulli's equation, okay? Now here, P1 upon gamma plus Z1 is the piezometric head at point 1, okay? And this I can write here as H1. This P2 upon gamma plus Z2 is the piezometric head at point 2, and this I can write here as H2. Okay, so I can say here H1 minus H2 will be equal to V2 square upon 2G minus V1 square upon 2G. Okay, so this is what's written here. H1 minus H2 is equals to V2 square minus V1 square upon 2G. Right? Till this step, it is clear? Okay, now it was mentioned in the question that the velocity at the throat is my 2. So what I'm saying is that V2 is twice of V1. Okay, it was mentioned in the question, this condition. Okay, so now I can apply this condition. So I can substitute the value of V2 into this equation. So it will become 2V1 whole square means 4V1 square minus V1 square. So that will become 3V1 square divided by 2G. Okay, so V1 will be equal to, now I can just simply readjust the equation. So put V1 on one side of the equation, other variables on the other side of the equation. So we'll get V1 square will be equals to 2G upon 3 into H1 minus H2. Okay. And if I want to find, since I want to find the velocity at the throat, I need to find this V2. So V2 equals to 2V1. So it will be 2 into V1. There. Now here H1 is known, H2 is known because it was mentioned what are the piezometric heads. Piezometric heads were given. Okay, at 1 and 2. So I can simply directly substitute the value of H1 and H2. G is acceleration due to gravity. So I can find what is the velocity at the throat. Okay, so just substituting the values, you're going to get that the velocity at the throat comes out to be 3.62 meter per second. So what do we did? We actually used a Venturi meter in a pipe flow to measure the pressures. And then using those pressures in the Bernoulli equation, we find out the velocity. So as I told you, Venturi meter is a simple device which can be used to measure velocity, which can be used to measure pressures, which can be used to measure the flow. Okay. So this is, and practically you have already done the experiment of Venturi meter in your lab. So probably you do have the understanding how to calculate the flow using the Venturi meter. So this was just a simple explanation of Bernoulli's equation. Obviously, when we are applying the Bernoulli equation, we are ignoring the fact that when the fluid which is flowing through the Venturi meter is made up of boundaries, and at the boundary there will be viscous effects. So we are ignoring those viscous effects right now because we cannot apply the Bernoulli equation if it is a viscous flow. So obviously, the velocity which we calculate from the Bernoulli equation will not be 100% accurate. It will be, there will be some inaccuracy because the real flow will be viscous, but we are ignoring the viscous effects because we cannot apply the Bernoulli equation to the viscous flow. We can apply it only to the inviscid flows. Okay, but still, to a great extent, this is a correct estimation, okay, by considering the assumption that it is an inviscid flow. So this was the solution to the problem. Is there anything within the solution of this problem which is not clear to anybody? Please feel free to ask. Everything's clear so far? So now let's try to solve this problem. An open tank filled with water and drains through a port at the bottom of the tank. The elevation of the water in the tank is 10 meters above the drain. The drain port is at atmospheric pressure. Find the velocity of the tank in the drain port. This is the situation we have. So we have a tank here. This is a tank. This is the tank. The tank is open to atmosphere. The tank is open to atmosphere, and there is a hole, a drain port at the bottom of the tank. Okay, it's not exactly at the bottom, slightly above the bottom. Okay, but what's happening is that the water is now coming out of this drain port. Okay. Now, what is mentioned is that the difference in the elevation of the water level in the tank to the drain port, this difference is 10 meter. This is mentioned in the question. How much it is? The elevation of the water in the tank is 10 meter above the drain. This is mentioned. Okay. Drain port is at atmospheric pressure. This is mentioned. Where the water is going out. So outside we have an atmosphere. Okay, so this is PF, atmospheric pressure. And obviously this tank is open to atmosphere, so here also we have atmospheric pressure. Okay. Now the thing is that when the fluid is coming out of the tank, so most of the fluid is moving in the same direction. Okay, so there are no relative motions between the layers of the fluid. All the layers of the fluid almost are moving at the same velocity. Only the thing is that it comes close to the boundary when it comes close to the drain. So viscous effects becomes important there, but right now we are ignoring the viscous effects, knowing that our calculation will give us little error, but we are accepting that error for now, just so that we can apply the Bernoulli's equation and see the solution using Bernoulli's equation. Remember, Bernoulli's equation cannot be applied over viscous flow. Wherever the viscosity effects are there, Bernoulli equation cannot be applied there. So in order to apply Bernoulli equation, we always have to assume that the fluid is inviscid, no viscous effects. This flow is steady. There is no change in the fluid flow with time. Okay, the fluid is incompressible, so probably it should be liquid, not gases. And the flow should be along the streamline. Okay? So then we can apply Bernoulli equation at any point within the fluid. So what we do is that we can apply the Bernoulli equation at 2 points. One point is top of the tank here, and the other point is at the drain. So this will be my point 1, this will be my point 2. So I can apply the Bernoulli equation between these 2 points. And obviously there is a continuous motion of the fluid from 1 to 2. So it's a connected fluid motion. Okay, so it's not being disconnected anywhere from 1 to 2. So it's along the streamline. Okay. So I can apply it between 1 to 2, and I can see that how can I apply the Bernoulli's equation in this case. Okay. So what do I need to find out? I need to find out what will be the velocity at 2. Okay. What is required is that find the velocity of the liquid in the drain port. So at the drain, what is the velocity? If I'm saying that my drain is 0.2, so I need to find what is V2. Okay. Before moving towards the solution of the problem, first of all, do you understand the problem statement and the figure? Is there anything within the figure or the problem statement which is not clear? Okay. Now let's move over to the solution. Okay. One thing is that I've already explained why we can apply the Bernoulli's equation. Okay. We can apply the Bernoulli's equation because we are assuming that this flow is steady. We know that it is water. Water is considered incompressible. Okay. We are applying the Bernoulli's equation between point 1 to 2. Point 1 to 2 is continuous fluid motion. It is along the streamline. And we are applying the Bernoulli equation, assuming that there are no viscous effects throughout from 1 to 2. So the Bernoulli's equation is applicable. Okay. So once we have determined that Bernoulli's equation is applicable, now we can apply the Bernoulli's equation. The Bernoulli's equation from point 1 to 2 will be this. It says that the summation of 3 different pressure heads will be same from point 1 to point 2. Okay. So now let's try to figure out one by one. Okay. So point 1 was open to atmosphere. So pre-atmospheric pressure, what will be the gauge pressure? 0. Right, atmosphere, the gauge is 0. Okay, so I can say that P1 will be 0. P2 is the drain point. Where is the drain going? To the atmosphere, outside. So it's also 0. Okay, so let me this first. P1 0, P2 also 0. Okay. Okay, we want to find out what is V2. This is that we want to find out what is V2. But we know one thing, that we don't know what is V1. We don't know what is V1, but we know one thing, that V1 will be very, very small compared to V2. Because V1 is the level of the water going down in the tank, and V2 is the velocity of the water coming out of the drain. The velocity of the water coming out of the drain will be very fast compared to the level of water going down in the tank. Okay, so we don't know what is V1, but we know that V1 will be very, very, very small compared to V2. So if something is very, very, very small compared to the other value, and here we will be using not just V1, V2, we'll be using their squares. Okay, so we are using V1 square, V2 square. So if we know that V1 is very small to V2, then V1 square will be very, very small to V2 square. Right? So we know that 2 is very small to 200. So what about their squares? 2 square will be 4, and 200 square will be 200 into 200. So their squares will be very, very, very small. So if we know that V1 is very small to V2, then V1 square will be very, 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 very small than V2 square. So we can ignore V1 square. We're ignoring it because its value will be very, very small. Okay, so it will be like just giving you the example here. So that the difference between 2 and 200 is also too much, but then the difference between 200 square and 4 is significantly high. Okay, so this is the idea. So we ignore V1. So what do we left up with? Z1, Z2, and V2 square upon 2G. We need to find V2. Okay, so let's put V2 on one side of the equation. So now we are going to be left up with this thing only. This is what we are left up with. This equation. Okay. Now in this equation, just take V2 on one side of the equation, the remaining things on the other side of the equation. So we get 2G Z1 minus Z2. Now Z1 minus Z2 is just the elevation difference between the drain port and the level of water in the tank. So if you look here, 1 was the water level in the tank, 2 is the drain port. So Z1 minus Z2 is basically the elevation difference here. Okay. And it is already mentioned in the question that it is 10. The elevation of the water in the tank is 10 meters above the drain. It's already mentioned what is Z1 minus Z2. That is 10. So we know this term from the question is given. G is acceleration due to gravity. So now we know everything. Just substitute the values. You're going to get what is the velocity at the exit of the drain. So in the drain port, the velocity would be around 14 meters per second. We do know that the actual velocity will be a little different than this because we are assuming some of the things which are not in reality. Yeah. So we are assuming that there are no viscous effects. Obviously, there will be some viscous effects, but we are assuming that there are no viscous effects. So there will be some error in this calculation, but still, it's a reasonably correct value. So this is how we calculate the velocity at the exit of the drain port in this numerical. Is there anything within this numerical which is not clear within the solution here? If there is anything, please let me know. Everything is clear so far? Now let's talk about some more applications of Bernoulli's equation. We have a stagnation tube. We can apply Bernoulli's equation along the stagnation tube. Now, first of all, what is a stagnation tube? Look, suppose if I have a pipe and the fluid is flowing through the pipe. Okay. What I can do is that I can attach a pipe here small pipe, and this is the piezometric pipe. Okay, because of this piezometric pipe, some of the fluid will enter into the pipe. Okay, and we can find out what is the level of the fluid entered into the pipe, so that we can find out what is the hydrostatic pressure within the pipe. Okay, now suppose what we do is that instead of just putting the pipe over a pressure tap, you see here, this is known as a pressure tap, because you have a pipe and you are putting some holes in it, and these are the pressure taps, so that you can connect another pipe to this, another tube to it, to find out the hydrostatic pressure. Now, instead of just connecting a single tube, what I do is that I connect a tube in this way. Okay. Now what will happen? Previously, some of the fluid was just entering into my tube, okay, but without stopping any streamline motion. But now, because of the tube insertion in this way, there will be a stoppage in the streamline motion. One of the layer of the fluid, which is going to come in contact with this tube, will have to stop at certain point. Why? Because it will enter into the tube from here, the regular layer of the fluid flow, okay, and obviously it cannot go escape out this pipe, okay, so it will stop. So now I'm actually stopping the specific motion of the fluid layer. Okay, I'm not just making a random fluid molecules to enter within the tube, but I'm specifically stopping the motion of a fluid layer. The rest of the fluid will flow. Rest of the fluid will flow from the sides. Okay, but one of the layer is going to stop. Okay, and so this is known as a stagnation tube, because it stagnate one of the layers of fluid. Stagnate means stop it, make it stationary. So one of the layer of the fluid which was previously in motion has to stop, because it has to enter within this pipe. Okay, and so that's why we call this as the stagnation tube. Now, stagnation tube has a specific factor that it reduces the velocity of that specific layer of the fluid from whatever the velocity it had to zero. So the velocity will stump down to zero for that specific layer. Okay, and so this is known as a stagnation tube. Now, what we can do is that we can apply the Bernoulli's equation to that specific layer of fluid. Okay, now suppose consider this fluid flow here. Now here, this is the stagnation. This is a stagnation tube. Now here, this is a stagnation tube. Consider this specific layer of the fluid, which is moving in this direction. At this point, when it is at point 0, there is a certain velocity. But by the time it reaches point 1, the velocity has to be 0 at this point. This fluid motion of this specific fluid layer has to become 0 velocity when it reaches at point 1. Why? Because this is the point after which it cannot flow further. The fluid has filled this region, and now fluid cannot escape out. Okay, so obviously this is a stationary. This whole fluid column till this point is a stationary. Okay, so we have halted the motion of the fluid layer. We have stopped it. Okay, so at state point 0, at point 0 in the fluid motion, there was some velocity, but at point 1, there is no velocity. This is the stagnation point. This is the stagnation point when the fluid velocity drops to 0 because of some hurdle. Okay, so but we can apply the Bernoulli's equation between point 0 to 1. Why we can apply the Bernoulli's equation? Assuming that the flow is steady. Okay, there is no change of fluid and motion velocity with time. This is a liquid motion. This is a liquid flow, so it is incompressible. There are no viscous effects. Why no viscous? All the layers of fluids are moving in the same velocity. Okay, and it is along the streamline. So all these factors, we can presume them. We can assume them, and we can actually apply the Bernoulli's equation between point 0 and 1. Okay, now if we apply the Bernoulli's equation between point 0 and 1, so how would that application be? Let's have a look at it. Okay, so first of all, between 0 and 1, there won't be any elevation difference. We are both, this is a horizontal flow. So between 0 and 1, there is no elevation difference. So Z1 at this point and Z0 or Z0 at this point, they both will cancel each other because they are at the same elevation. Okay. Now what we are left up with is P1 plus rho V1 square upon 2 equals to P0 plus rho V2 V0 square upon 2. Okay. Now here we know that it's state at point 1, the velocity is 0 because that's the stagnation point. So we know that V1 is 0. So we can put this V1 as 0. Okay. So what are we left up with? We are left up with V0 equals to 2 P1 minus P0 divided by rho under root. Okay. So with the help of a stagnation tube, I can find out the velocity. With the help of piezometer tube, I was not able to find velocity. I can only find out the hydrostatic pressure with the help of piezometer tube. But with the help of a stagnation tube, I can find out the velocity. Because the stagnation tube is actually stopping the motion of a fluid layer. Piezometer tube was not stopping the motion of the fluid layer. Some of the fluid molecules entered into the piezometer tube, but it was not stopping any fluid layer motion. But the stagnation tube actually is within the flow, in the direction, in the path of the flow, so it stops one of the layer of the fluid motion. And when it stops, that means we know that earlier there was some velocity. At the time when it enters into the stagnation pipe, the velocity goes to 0. So we know there is a velocity variation. We know there is a velocity difference. Okay. So correspondingly, we can find out what will be the velocity by using the Bernoulli's equation like this. Okay. So we have here, see here, this one was the piezometric pipe. And this is the stagnation pipe. Okay. Stagnation pipe can be used to measure velocity. Piezometric pipe cannot be used to measure the velocity. So this is one of the difference. Obviously, now you might have some idea that I can give some conceptual theoretical questions in the exam, like I gave in the mid-exam, like I will give in the final exam. Okay. And they won't be beyond the things which I will explain that, okay, I mentioned in the lecture that, okay, I can give this from this point. So this is one of the point. What is the difference between the stagnation tube and the piezometer tube? I have confidence in you guys. So stagnation tube, it is also known as total head tube because it actually stops the motion of the fluid completely. So the kinetic head also goes to 0. So this is so whatever the head this provides also have the kinetic effect into it. Okay. So suppose if I have two tubes here, attached to this pipe, one piezometric tube, other is the stagnation tube. The difference in the elevation of the two tubes are going to give me the kinetic head because that's the only difference. Okay. So hydrostatic pressure and the elevation effect was both there in the piezometer tube, but only the velocity effect was not there, which will be taken up by the stagnation tube. The difference in elevation between the stagnation tube and the piezometer tube will be the actually velocity head. That's the only difference. So what's the difference between a stagnation tube and piezometer tube? Where it is used? Why it is used? These are some of the questions which I have already answered you. Okay. And these are some of the questions which I might be asking you if I have to during the exam. Conceptual questions. So you can just substitute the values. Since P0, it will be gamma D. If this is the distance D, this is the distance L. Then P1 will be gamma into L plus D. So just substituting the values, you're going to get V0 equals to 2GL. That will be the formula. Now, there is a difference. I can use the stagnation tube to find out the velocity, but there is a problem. Because stagnation tube will have the fluid level attained within the tube according to whatever the pressure I have in the main pipe. Now, if I have a very pressurized pipe, then I need a very huge stagnation tube. Literally almost for a very, very pressurized pipe, it is almost impossible to have a tube equal to the size of a building. That's not feasible. That's not practical. Okay. So stagnation tube can measure the velocity if the fluid remains within the tube, does not come out of the tube because of the very high pressure within the pipe. So there is a limitation. Now that limitation is removed if we use another device which is known as Pitot tube. Pitot tube. Now Pitot tube is also a device to measure the velocity using the pressures, but it has a specific construction such that the Pitot tube can be connected to a differential manometer, and then the differential manometer is just going to give us the difference between the overall head and the piezometric head. The difference between overall head and the piezometric head is the kinetic head. So if I get the kinetic head, I can directly get the value of the velocity. Okay, so it does not matter how high is the pressure in the pipe, because the difference between piezometric head and the total head will only be the kinetic head. So I need to have a differential manometer connected just enough so that it can provide the value of the kinetic head without taking into regard how much is the hydrostatic pressure itself within the pipe. I don't care how much is the hydrostatic pressure in the pipe now. Okay, so this is possible by using the Pitot tube. Now let's see the construction of the Pitot tube. Now Pitot tube have basically two tubes, one inside the other. It is constructed of two tubes, one inside the other. So let's see the construction here. So you see here, the fluid is coming, let's say fluid is coming from the bottom in this way. The fluid is coming. Now I have one tube, which is the inner tube, another tube, which is the outer tube. Okay. Now the fluid can directly enter into the inner tube, but cannot enter into the outer tube from here because it is sealed. The fluid can directly enter into the inner tube, but cannot enter into the outer tube because the outer tube opening is sealed here. Okay. However, what I do is that in the outer tube, I put some openings. These are some of the openings. So the fluid which is moving in this direction, some of the fluid from this direction is going to enter into the outer tube from these openings. Now, what's the difference? The fluid which is directly entering into the inner tube will also have the kinetic head in it, because it is in the direction of the flow. The kinetic head is also going to enter into it. However, the fluid which is going to enter from the taps on the sideways of the outer tube, that fluid can only enter without the kinetic head, because the kinetic head is in a specific direction, and the tap open on the outer tube is perpendicular to that direction. So the direct velocity of or the direct velocity head cannot enter into the outer tube. Okay, so only the hydrostatic head and the elevation head is going to enter into it. Okay, so now the inner pipe is connected to one end of the differential manometer, and outer pipe is connected to another end of the differential manometer. Okay, so the difference between the two ends of this pipe within this differential manometer is going to provide us how much is the kinetic head. So the only difference is that in the inner pipe, the whole fluid is entering, along with the hydrostatic head, elevation head, and kinetic head. In the outer pipe, kinetic head cannot enter, because kinetic head is direction dependent. If the fluid is moving in this direction, kinetic head is going to move in this direction. And so the fluid particles which are actually entering into the outer pipe from the sideways, they cannot have the kinetic head along with it. So only hydrostatic head and the elevation head will be entering into the outer pipe. So one end of the outer, so one end of the differential manometer is connected to the outer pipe, other end of the differential manometer is connected to the inner pipe. So the difference in the elevation which the differential manometer is going to give is just the kinetic head. Okay. The hydrostatic head and the elevation head are cancelling each other because they are entering in both the pipes. So they are entering on one side of the differential manometer, they are also entering on the other side of the differential manometer, they are cancelling each other. So irrespective how much is the hydrostatic pressure, because it will cancel each other. We are now not much concerned about it. The only thing is that how much is the velocity head that could be measured by the differential manometer. Okay. So anyways, I tried to explain you this concept, but I have no idea whether you understood it or not. I hope you will. Anyways, we can have a Pitot tube connected to a pressure gauge direct. So differential pressure gauge can also give you the readings, or you can have a differential manometer, which can also give you the reading. Because we have already solved how to solve problems related to differential manometer and differential pressure gauges in the last chapter. So I'm pretty sure that you know how to do it. Anyways, now we can, if we can simply, okay, this equation we're going to come to it in later as well. So we'll drive it later. So anyways, the equation for finding out the velocity using the differential pressure gauge will be 2 del P over rho under root. Okay. This formula we are also going to drive later on. So let's see this numerical. Application of Pitot equation with manometer. A mercury manometer is connected to the Pitot static tube. A mercury manometer is connected to the Pitot static tube. Why it is said mercury manometer? Because inside the manometer, the fluid of the manometer fluid is mercury. Okay. A mercury manometer is connected to the Pitot static tube in a pipe transporting kerosene as shown. So you have a pipe here. This is the pipe, and there is kerosene flowing through the pipe. So you have here kerosene. What is kerosene? Kerosene, oil. Matti ka tel. Yes, matti ka tel. So matti ka tel guzar raha hai is pipes. So what I do is that I need to find out what is the velocity of matti ka tel in the pipe. What is the velocity of kerosene in the pipe? Okay. So if the deflection on the manometer is 7 inches, deflection on the manometer is 7 inches. What I do is that I put a Pitot tube. This is a Pitot tube. There are two ends of the Pitot tube. One end of the Pitot tube is connected to one side of the manometer. Other end of the Pitot tube is connected to the other side of the manometer. And the manometer is showing a deflection. Why? This is a deflection. Okay, and how much is this deflection? This is how much is this deflection? This is actually 7 inches. Right? Now, what is the kerosene velocity in the pipe? We need to know what is the velocity here, kerosene in the pipe. Assume that the specific gravity of kerosene is 0.81. So we have specific gravity of kerosene, okay, which is 0.81. Okay, before moving towards the problem solution, first of all, do you understand the problem statement? You have a pipe, kerosene is flowing through the pipe. What I do is that, what I want to know how much is the velocity of the kerosene in the pipe. I put a Pitot static tube. Connect the two ends of the Pitot static tube with the differential manometer. Now the differential manometer is showing some deflection. How much the deflection it is showing? 7 inches. This differential manometer is basically filled with mercury here. So the mercury is showing a deflection of 7 inches. Now I know this thing that the deflection is 7 inch. And now I want to use this measurement to find out the velocity in the pipe. How do I get this measurement? By connecting a manometer to Pitot tube. Pitot static tube. The full name is Pitot static tube. So before moving towards the solution of the problem, the first thing is that, do you understand the problem statement? Anything within the problem statement which is not clear? Do you understand this figure? Once again, see the picture of the Pitot tube, okay, just so that you can remember. Okay, the Pitot tube is constructed of two tubes, one inside the other. The inner tube is put in the direction of the fluid flow, so the fluid flow can directly enter into the inner tube. Outer tube is sealed at this point, so the fluid flow cannot enter directly into the outer tube, but there are openings. There are openings sideways, sideway openings. Through the sideway openings, the fluid is going to enter into the outer tube. Okay, so one end of the outer tube will then be connected to one end of the manometer. The other end of the other end of the manometer will be connected to the inner tube. Okay, so inner tube is taking the whole fluid, the whole head, hydrostatic head, elevation head, plus kinetic head. Outer tube is taking hydrostatic head and elevation head, but not the kinetic head, because the fluid is entering sideways and velocity is directional. So if the fluid is entering perpendicular to that direction, there is no component of velocity in that direction. So the kinetic head will not be there. Okay. So if we just measure, so the differential manometer is just going to give us how much is the difference between this. So that difference is the kinetic head. How much is the kinetic head? Okay. So now coming back to our problem. So we have a situation like here. So fluid was flowing like this. So we put the Pitot tube here in this way. So the inner tube will be just, so the fluid will be entering the inner tube from 1, okay, which should be put directly in the direction of the flow. Okay, and the fluid will be entering the outer tube from 2, which is not in the direction of the fluid flow, but sideways opening. Okay. So now what I can do is that I can develop, because this is still a continuous fluid flow, this is still a continuous fluid medium. Okay, we can apply the Bernoulli's equation between point 1 and point 2. I can apply the Bernoulli's equation between point 1 and point 2. Okay. So from 1 to 2, there is no direct path. 1 to 2, there is no direct path. Try to understand this thing here. If suppose, look here, if suppose I am here at 1, if suppose I'm here at 1 and I want to reach 2. So what I'm going to do is there, I'm going to enter into the smaller pipe, will pass through the smaller pipe, go into the differential manometer, come back from the differential manometer, get connected from the outer pipe, then return back until I reach point 2. Right? There is no direct path from 1 to 2. You have to pass through the inner pipe, then go through the differential manometer, then come back to the outer pipe, then reach to point 2. Okay. So this is where we are going to solve the problem from 1 to 2 when we are going to apply. Okay. So now let's see the now let's see the equation, pressure equation that we made. Okay. Let's start from 1. Okay. So we'll have P1. Then we are moving down. How much down? P1 plus Z2 minus Z1, this much down. We are going this much down. Plus Z2 minus Z1 into gamma caron C. Okay. Then we are moving further down from here till, because the fluid is going to enter from here and then goes into one side of the manometer till this point. So the elevation difference here is L. Then L into gamma kerosene. These are all plus. Why? Because we are moving down. Now, once we have reached this point, now we can directly jump from this point to, we can directly jump from this point to this point, because fluid pressure remains constant in the horizontal direction. Okay, so then now we are moving up. Okay, so negative sign. So negative y into gamma Hg, because here I have mercury here. Then further negative this distance till reach point 2. So this distance will be how much? L minus y. Minus L minus y into gamma kerosene will be equals to P2. So I have just written the pressure equation from 1 to 2, but by passing through the Pitot tube. One might say, why I didn't make the equation just directly from 1 to 2? Because there was no direct path. You have to enter into the smaller pipe, inner pipe, exit the Pitot tube, enter into the manometer, then return back from manometer to the outer pipe, and then from outer pipe to point 2. Because this is the construction of the Pitot tube, as per the construction of Pitot tube. Okay? So I have just here made the equation from P1 to P2. Is this equation clear or not? Now L is from point 2 to this. वापस जाएगा. 1 से 2 फ्लूइड डायरेक्टली नहीं जा सकता. 1 से जाएगा, पहले इनर पाइप को क्रॉस करके मैनोमीटर में एंटर होगा, फिर मैनोमीटर से दोबारा क्रॉस करके आउटर पाइप में जाएगा, और फिर उसके बाद आएगा. Okay. So now we have this equation. This is the equation. What I can do is that I can rearrange some of the terms. Okay, I can rearrange some of the terms. So P1 plus gamma kerosene Z1 I can put as one group, because I know this is the piezometric pressure. If I add hydrostatic pressure with the elevation pressure, that becomes the piezometric pressure. Okay. Also, I can add P2 with gamma Z2. That will be again piezometric pressure at 2. Okay. The remaining will be this term. So we'll have PZ1 minus PZ2 equals to Y. Y is the deflection into gamma Hg minus gamma kerosene. Okay. We got this equation. This is just rearranging the main equation. Okay. Then, as I told you that we have the original. Okay, original also let's have a look at this original equation. We didn't go through this original equation first, but let's have a look at the original equation here as well. Between point 1 and 2, 1 is the point in the lower pipe, in the inner pipe, and 2 is the point in the outer pipe. Okay, of the Pitot static tube. If I apply the Bernoulli's equation between 1 and 2, okay, I know at 1 velocity will be 0. Because the whole pipe will be entering, the whole flow will be entering into the into this pipe. So it should be the stagnation point. Should be the stagnation point. Velocity will go to 0. At V2, velocity will not be 0. Okay, because the velocity direction is perpendicular to the opening. Okay, so none of the fluid is going to enter. The direct fluid motion will not be there. Okay, so V2 will not be 0. So if I put V1 0, so this term goes 0. Okay, so here P1 plus gamma Z1 is basically PZ1, and P2 plus gamma Z2 will be PZ2. So what we are left up with, B equals to 2 into PZ1 minus PZ2 divided by gamma, divided by rho. So this becomes the formula for velocity using the Pitot static tube. Okay. Now this PZ1 minus PZ2 is something that we have developed in this numerical as well. Okay, so this is what? PZ1 minus PZ2 equals to Y gamma Hg minus gamma kerosene. This we have find out. Okay, so now I'm just going to substitute it here. Okay, so V was equals to 2 Pz1 minus Pz2 divided by rho kerosene and rho under root. This is the formula that we saw here, right? 2 Pz1 minus Pz2 divided by rho under root. Okay. Now Pz1 minus Pz2 is something that we have already determined. This is basically what? This is Y into gamma Hg minus gamma kerosene. Just substitute the value here. Y into gamma Hg minus gamma kerosene. This thing. Once you substitute it into this main formula, you're going to get the velocity here. Substitute the values. Velocity comes out to be 24.3 feet per second. So here you need to know three things. What is the specific weight of mercury, which is used in the manometer, and what is the specific weight of the kerosene, and how much is the deflection in the manometer. Three things. So if you know three things, just substitute the values into the main equation, and you're going to get how much is the velocity of the kerosene in the pipe. So using the Pitot static tube and applying the Bernoulli's equation, we have actually determined what is the velocity of the kerosene in the pipe. Is it clear? Is there anything within the solution of this problem which is not clear? Please feel free to ask. This is actually a very good and a very important question from the exam point of view. Because it is combining the concepts of developing pressure equation with the velocity equation using Bernoulli's, combining them together to actually find out the velocity. So it's a very good question where you have 2 or 3 concepts combined together in a single problem. Normally in the exams, it's always preferable to have questions where 2, 3, 4 concepts are combined together into the same problem. Most of the time, these things come in the homework problems. Okay, before moving towards the next problem or the next topic, I first want to ask, is there anything within this topic, within this numerical, within the solution, which is not clear to anybody? Please feel free to ask. मैनोमीटर पाइटेट स्टैटिक ट्यूब हमें लगाना है. अगर हमें वेलोसिटी मेजर करना है, पाइटेट स्टैटिक ट्यूब लगाना पड़ेगा. अगर हम पाइटेट स्टैटिक ट्यूब लगा रहे हैं तो उस पाइटेट स्टैटिक ट्यूब का एक एंड होता है जो ओपन होता है. अगर आप पाइटेट स्टैटिक ट्यूब लें, खरीदें मार्केट से, तो एक एंड ओपन एंड नजर आ रहा होगा. आपने क्या करना है कि जो फ्लो है पाइप का, जिस डायरेक्शन में फ्लो है, बस पाइप ऐसे लगाना है कि फ्लो उसके अगेंस्ट जा रहा हो. ऑटोमेटिक वो एल शेप होता है. दूसरे एंड पर आपके पास 2 ओपनिंग्स होंगी. एक ओपनिंग को आप एक एंड डिफरेंशियल मैनोमीटर, दूसरी ओपनिंग को दूसरे एंड डिफरेंशियल मैनोमीटर में लगा देंगे. दोनों के दरमियान डिफ्लेक्शन आ जाएगा. और ये जो पाइप का दूसरा एंड है, उसको आपने बस मेजर पाइप के अंदर इस तरह डालना है कि वो अगेंस्ट द फ्लो, उसको रोकना बस. Is it clear? Did I answer your question? I don't know. Did you did numerical related to Pitot static tube in your fluid practicals lab? No. Okay, Pitot static tube. If we do not use the manometer, if we directly use the differential pressure gauge, then it becomes quite simple. You don't have to develop the equation of the pressure from point 1 to point 2. You directly have, suppose if I have air flowing through the fluid, air flowing through the pipe, and I put a differential pressure gauge connected with with the Pitot tube. Okay, so here this is a question. Differential pressure gauge is connected across the taps of a Pitot static tube. When this Pitot static tube is used in a wind tunnel test, the gauge indicates a del P of 730, the pressure difference of 730 Pascal. What is the air velocity in the tunnel? The pressure and temperature of tunnel are 98 kilopascal absolute and 20 degrees centigrade. So I can substitute the values of pressure and temperature to find out what is the density of the air. Okay. Now, if I know the density of the air, then simple formula is V equals to 2 del P over density. That was the formula we developed for the Pitot static tube, right? There. V equals to 2 del P over rho, or here 2 PZ1 minus PZ2 is del P over rho. Okay, so here there's the pressure gauges, since the differential pressure gauge is directly giving us the value of del P. So just simply substitute that value. So here 730 Pascal, you can substitute it directly here. Then density I have calculated, substituting density into the main equation, I can get what is the velocity. So using the differential pressure gauge, the problem becomes quite simpler and not a suitable candidate for exam. Because for the exams, it has to be a pretty heavy problem, right? So, but anyways, it does not mean that I might not be able to give this in exam as well. Okay, so you should prepare everything. Okay, so the next topic is rotational motion of the flowing fluid. Before this topic, do you want a break? Okay, let's have a break of 10 minutes. By 4:30, we will start back. Okay, so let's start with our next topic, which is the rotational motion of a flowing fluid. Concept of rotation. Rotation is defined as the average rotation of two mutually perpendicular faces of a fluid element. So suppose if I have a fluid element with two mutual perpendicular faces as A phase and B phase, so if there is rotation, then the angle between them is going to change. So initially the angle was like 90 degree. Now the angle is going to change, become less than 90 degree. So then you'll consider it to have rotation. Conceptually, if I have a fluid element, this is, let's say this is a rectangular fluid element, and this fluid element was at a certain angle such that the angle of the face A was theta A, and the angle of the face B was theta B. Okay, theta B and theta A would have been same initially, because we are saying that this is a perpendicular face element. Okay, so whatever the change in the angles, rate of change of that angles, average rate of change of these angles of perpendicular faces will be the rotation rate of rotation. So we define theta dot as theta dot is equals to half theta A dot plus theta B dot. So what is the rate of change of angle of A and what is the rate of change of angle of B, and the ratio average of that change is basically the rate of rotation. So suppose if theta A and theta B are not changing, then in that case, the angle between theta A and theta B would remain 90, and that means this is an irrotational flow. So irrotational flow is a flow where the rate of rotation is 0, means theta dot will be 0. Now here's something you have to understand, which is a little different from from the previous concepts. You can have something in translation. Translation means it's a linear motion, but there could be curvilinear translation. Linear motion in a curve. Okay, it is still not rotation. Rotation is when you have angular deformation of the fluid elements. If the fluid elements are angularly deforming, then you have rotation. Otherwise, we don't say that there is rotation. Okay. So suppose if I have this fluid element, the fluid element was moving in this direction. So looks like it is rotating. But if the fluid element has its faces and those faces are still keeping the 90-degree angle, the fluid elements are not deforming, then we will not call it rotation. And it is still rotational, although it looks like that it is moving in a circular pattern. So it's moving in a circular pattern, but irrotational. Rotation is only when the fluid element is deformed. Okay. So suppose if the fluid element was like this, the dotted square, now it deformed. This end becomes like this end becomes like this, so there is deformation. So the concept of rotation is that we need to find out what is the rate of rotation. Okay, so rate of rotation will be theta dot, which is half theta A dot plus theta B dot. Now theta A dot will be the it will be the change in the velocity with x, because the face is moving in the y direction but actually deforming in the x direction. Similarly, theta B will be theta B dot will be the change in the velocity in u direction, okay, with respect to y. Okay. However, there is a negative sign here. Why? Because these two changes are opposite to each other. Okay, so one is making a counterclockwise motion, other is making a clockwise motion. So they're opposite to each other in this deformation. So that's why there's a negative sign here. So anyways, this is defined as theta dot, and for this we define it as we also define it as omega z. So omega z is the rotational velocity component in the z direction. So rotational velocity component in the z direction will be half dava v by dava x minus dava u by dava y. So if you have omega z, then you can also have omega x and omega y. So this will be the omega x component, this will be the omega y component. Easy way to remember is that write x, y, z. Then if this is omega x, then for the y, write the z component value of velocity. For the z, write the y component of velocity. Or I can write here y, z, x. So this will be omega y, and here I'm using dz, so it should be having the u component of the x component of the velocity. And here I'm using dx, so it should be having the z component of velocity. So dava omega. Anyways, this is a short way of remembering it. So this is the rate of rotation vector. So rate of rotation vector will be omega x plus omega y plus omega z. Okay. So when I say that it is an irrotational flow, so these omegas will be 0. This will be 0. So when I say omega will be 0, means omega x 0, omega y 0, omega z 0. And if I'm saying omega x 0, that means dava v by dava x equals to dava u by dava y. When I say omega y 0, then we'll have this relation. When I say omega z 0, then I'll have this relationship. Okay. The most extensive application of these equations is basically the ideal fluid flow. We are not going to go through the ideal fluid flow. It's basically a graduating course, post-graduation course. So if we want to know if the flow is rotational, then for these, for an irrotational flow, these conditions must be met. If these conditions are being met, then we will consider it as a rotational flow. Otherwise, they are the rotational flow. We define another term as vorticity. Now, what is vorticity? Vorticity is just twice the omega. Omega was having half value. So if you just multiply it by 2, so the half factor is going to go. And so this is known as vorticity, omega. Yeah. So let's have a simple problem here. The vector v equals to velocity vector is 10xi minus 10yj. Represents a two-dimensional velocity field. Is the flow rotational? Is the flow irrotational? So if the flow is irrotational, then dava u by dava y should be equals to dava v by dava x. Now here we have the velocity u component of the velocity. This is the u component of velocity, and this is the v component of velocity. Okay, so u component of the velocity is 10x, v component of the velocity is negative 10y. So dava u by dava y will be 0, dava v by dava x will also be 0. Since they both are 0, means they both are equal. That means that yes, the flow is irrotational. So I can make a very small modification in this numerical and I can give it to you. And in this way, in such a way that maybe the answer is that the flow is rotation. But if you do understand, it won't be difficult to solve it. This is the same vorticity equation, but in the cylindrical coordinates. I don't think we need to cover the vorticity in the cylindrical coordinates. Okay, let's discuss about vortex. Vortex is basically circular motion. Now here in fluid mechanics, we define two types of vortex. One is the free vortex, other is the force vortex. And you have observed both of them. Might not have actually focused over there, but you have observed both of them. For example, if I take a glass and put water into the glass, then I take a spoon and just rotate water in it, rotate the spoon. So what will happen? My water will start rotating. Okay. Now try to see the water in it. There is rotation. What do you see? At the edges. The water at the edges are at the high velocity or in the center? Think about it. You put water in the glass, you take a spoon, rotate it. What do you think? The water at the edges will be at high velocity or water in the center? Edges. Edges, you will, if you just watch the edges, you will find that the water at the edge is moving very fast compared to in the center. For example, let's say that the water is rotating right now, and you take a toothpick or anything, and you put it into the water. Where do you think that you will feel more pressure? In the center or at the edge? At the edge, water is moving very fast. Right? This is the force vortex. In case of force vortex, as you move away from the center, the velocity increases. Then we have a free vortex, and you have also seen a free vortex. Let me give you an example. You go into the kitchen, you have a kitchen basin sink, block the drain, stop the drain, fill the basin sink with water, then open the drain. Now the water will start draining down, and you might see that there is a whirlpool developing at the point where the drain is going on. Now, if you look at, here is also a vortex generated, but here if you look at the vortex, at the sides, the water are very slow, but in the center, you will find it is very quick. This is a free vortex. It's opposite to force vortex. Force vortex, the more you go away from the center, the higher the velocity. In the free vortex, the more you come closer to the center, there will be higher velocity. These are both rotations. And there are two separate kind of rotations. Why? Because whenever you have free vortex, it is not considered a rotational flow. It is irrotational. The fluid elements are not deforming. And perfect example is that if you have a free vortex, take a small piece of tissue paper or paper. The tissue paper will soak. So put a piece of paper, because it's thin, it's light, it will float, and put on the water. You'll find that the piece of the paper will be revolving, but will not be rotating on its own. It will be revolving like this. But if you have a force vortex, put a piece of paper there, it will actually revolve. That is a rotational flow, force vortex. Free vortex is considered a rotational flow. And there are two different forms of flow. Okay. In case of free vortex, as you move closer to the center, so free vortex velocity will be higher. So you can see when the water is draining out, you can see in the center, you will find velocity is very fast. And anything beyond, far away, you will find there is not much velocity, slowly moving. But if it is a force vortex, in case of force vortex, the more you go away from the edge, higher the velocity. And the more you come closer to the center, lower the velocity. Okay. So there is a difference. These are two separate phenomena. Almost everybody have observed these, but never focused over it. They are two separate things. So what is the difference between free vortex and force vortex? Keep that in mind to come as a short question in exam. Okay, whenever you have a force vortex, so for the case of force vortex, the velocity, the circumferential velocity, the velocity in the theta direction, okay, not along the radius. Okay, this velocity in the theta direction will be equals to r omega, you can say. Or you can say it will be CR. In case of free vortex, the velocity in the circumferential direction, v theta, will be C upon R. Okay. So the higher the radius, the lower will be the velocity. The more you go far away from the center, higher the radius, going far away from the center, lower will be the velocity for the case of free vortex. Okay. But in the case of force vortex, it's R omega. Okay. So the higher the radius, higher will be the velocity. Right? So here is a small description of it here as well. This is a force vortex. So we are at the more you go away from the center, the larger is the velocity. And the more you get closer to the center, smaller is the velocity for the case of force vortex. For the case of free vortex, it's opposite. The more you come closer to the center, it's larger velocity. So the free vortex, in case of the free vortex, the fluid elements are going around in circles, but they are not rotating. This is an important point. In case of free vortex, it is an irrotational flow. For the case of force vortex, it is a rotational flow. Why? Because in case of free vortex, the fluid elements are going around in circles, but they are not rotating. They are not angularly deforming. But in force vortex, they are actually rotating. There is an angular deformation between the fluid elements. Okay. There is a simple problem here. So we have a free vortex in air, rotates in a horizontal plane, and has a velocity of 40 meters per second at a radius of 4 kilometers from the vortex center. Find the velocity at 10 kilometers from the center and the pressure difference between the two locations. The air density is 1.2 kg per meter cube. Okay. So since it is a free vortex, so our formula will be V equals to C upon R. If it was force vortex, our formula would be V equals to R omega. That would have been the formula for the case of force vortex. But right now it is free vortex, so we're going to use this. Okay. So it's because C is a constant. Okay. So I can write here that V at 10 kilometer divided by V at 4 kilometer equals to R at 4 kilometer divided by R at 10 kilometer. That's basically V is inversely proportional to R. So I know what is the velocity. I know this is 4 kilometer. This is 10 kilometer. Obviously, 4 by 10 is 0.4. So I know what is the velocity at 10 kilometer or 4 kilometer. I know what is the velocity at 4 kilometer. Okay, so I can find out what will be the velocity at 10 kilometer. So the velocity at 10 kilometer comes out to be 16 meters per second. Okay. Now this is a free vortex. Free vortex is an irrotational flow. And whenever you have an irrotational flow, you can apply Bernoulli's equation. You cannot apply Bernoulli's equation over rotational flow, but can apply Bernoulli's equation over a rotational flow. So in free vortex, Bernoulli equation can be applied. Force vortex, Bernoulli equation cannot be applied. Okay. So we apply the Bernoulli's equation. So it's because it is applied on a horizontal plane. We are applying the Bernoulli's equation on a horizontal plane where the fluid elements are rotating. Okay. So we have the pressure at 4 kilometer. We have the pressure at 10 kilometer. Now we know the velocities at 4 and velocity at 10 kilometer. Okay. So we know the velocities at 4 and 10 kilometer. So we can find out what is the pressure difference between 4 and 10 kilometer on the horizontal surface. So it comes out to be 806 Pascal because we know the velocities. Now there's a question. We know practically that on a horizontal surface, the pressures should be constant. It should be the same pressure. But the pressure line, or you can say the constant pressure line, changes when the flow is rotating. A very simple example is that take a glass of water, take a spoon and spin the water. When the water is spinning, initially the water level was like this. When the water is spinning, the water level becomes like this. The more you spin in the center, it goes down, on the sides it goes up. So the constant pressure does not remain horizontal when the water is circulating. If you stop the water again, it will become horizontal again. But if you start spinning the water, in the center, it keeps on going down, from the sides, it keeps on coming up. So like, what do you say, like a dome, inverted dome. Okay, and larger you spin, the bigger the dome. So this dome is basically a constant pressure, you can say the constant pressure surface. But now the horizontal surface is not constant pressure. But if you stop the motion, the water will again become stationary and it will become a constant surface. Okay. So the pressure difference at 4 kilometer radius or 10 kilometer radius would be same if the water is not rotating. But if the water is rotating, then there will be pressure difference between 4 kilometer and 10 kilometer. You getting the idea? So anybody have any problem in understanding this question? It's a simple straightaway question. There's another one. You can go through it yourself. It's simple. This is for the case of, this is also for the case of free vortex. Wind velocity is 15 miles per hour is observed at a radial distance of 200 miles from the center of the storm. Determine the wind velocity at 100 miles and 50 miles, assuming the storm to behave as a free vortex. So if the storm is behaving as a free vortex, V is equals to C upon R. Or you can say C equals to RV. So you can find the value of the constant because you know the velocity and radius for one specific condition. Then at different radiuses, you can find out what will be the velocity. Let's talk about the actual tornadoes and whirlpools. Alhamdulillah, in Pakistan, we don't face tornadoes. But yes, those living outside, especially in the US, Canada, there are big tornadoes. Some are very deadly ones. So tornado is basically observed as a combination of free and forced convection, free and forced vortex. So there is a portion in the tornado which is a forced vortex, then there is a portion in the tornado which is a free vortex. So normally on a simplistic scale, when it is considered a tornado within the central region, the tornado is a forced vortex. But in the outer region, the tornado is a free vortex. Okay. So in the outer regions, the tornado behaves as free vortex. And then in the central core region, the tornado behaves as a forced vortex. This is the specific construction, or rather say the configuration of a tornado. Okay. Obviously, there are much more complications in it. This is by considering it on a very simplistic scale. So actual vortices, tornadoes, and whirlpools are approximated by a combination of forced and free vortices, with the forced vortex at the center and the free vortex on the outside. This statement is important from the conceptual short question point of view. What are tornadoes and whirlpools constructed of, made up of? Okay. And the other thing is that because of this specific construction of the tornado, the real destruction is not because of the fluid in the circular motion. The real destruction comes because of this tornado construction. We have a very low pressure region developed in the center. That low pressure region is so much low pressure that there is a specific tendency to suck everything up this central region. Okay. This is, we have a secondary flow here. This secondary flow here is being generated because of the low pressure region developed inside the tornado and the center region. And that secondary flow is the main reason for major destructions in the tornadoes. Because this has the capacity to suck up everything, whether there is a house, building, trees. Now, suppose if we have to apply the Bernoulli's equation in the rotational flows, first of all, it can only be applied if the flow is irrotational. For rotational flows, it cannot be applied. But if the flow is in the circular motion, if the flow is in circular motion but irrotational, we can apply the Bernoulli's equation. In that case, there will be only one change in the equation. The Bernoulli's equation was basically what? P upon gamma plus Z plus V square upon 2G. So instead of V square, we are just going to replace it by, because V is equals to R omega, right? We're going to replace it by R omega, so it becomes omega square R square. Okay. And then this equation can be applied, can be used in the Bernoulli's equation as a Bernoulli's equation. So therefore, the Bernoulli equation can be applied between any 2 points in the flow field if the flow is inviscid, steady, incompressible, but now it will not be along the streamline, but it will be for irrotational flow. So that's the only difference. If the flow was not irrotational, then Bernoulli equation can be applied if the flow is along the streamline. Okay, Bernoulli equation can only be applied along the streamline. But if the flow is in a circular motion, then it must be irrotational. Okay, then the Bernoulli's equation can be applied. Other three conditions remains the same. Has to be inviscid, has to be steady, has to be incompressible. Okay, so let's see a numerical here. A cylindrical container of radius capital R equals to 0.4 meter contains water up to a height of 0.5 meter. So this was the container. Suppose this was the container. So initially, when the water was there in the container, so what was the height of water in the container? That was 0.5 meter. Okay. And the radius of the container is how much? The radius of the container is 0.4 meter. Okay. And this is open to atmosphere. This is open to atmosphere. The container is now rotated about the z-axis at omega such that the water requires the configuration as shown in the figure. Now what we do is that we rotate the container. Somehow the container is being rotated. So with the rotation of the container, the water in the container will also rotate. Now when the water is going to rotate inside the container, what will happen? The center of the water is going to go down, the sides of the water is going to come up. And the rotation was so strong that it reaches to the point that the center goes down, down, down until there is a small region in the center where there is no water at all. So rotation was very fast, such that there is a small region in the center where there is no water at all. All the waters have gone towards the side. Okay. And this region is specifically defined by the distance A here. Okay. So the container is now rotated about the z-axis at omega, whatever the velocity was there, rotational velocity, such that the water acquires a configuration as shown in the figure. The length A is 0.2 meter. This length A is 0.2 meter. The surface of the water is parabola. Obviously, now this surface will be a parabola, whose equation is given by this. Now this will be the equation of the surface. Z is equals to H was the total height of the water plus omega square upon 4G into 2R. R is whatever the radius from the center, whatever the radius is, small r. 2R square minus capital R square. Capital R is the original radius of the container, which is 0.4. Determine the angular velocity. We need to find how much is this. And then what will be the Z max? Z max is this distance. So is there any specific velocity with which we can rotate such that the height Z can become max? So we need to find how much should be the Z max, what's possible. And what will be the pressure at point A? Point A is here. So we need to find what is the pressure at this point. Small r is basically this Z is given as a function of radius. So if you know at any point R, you can find out what is the Z at that point. So before moving towards the solution of the problem, first thing is that you understand the problem statement. So you have a container the container is filled with water, open to atmosphere. When it was not rotating, the height of the container is given, the radius of the container is given. Now, when you rotate the container such that there is a specific region, such that the water takes the form in a way that there is a specific region in the bottom that there is no water there. Okay, and this region is a length A equals to 0.2 meter. Okay, and in that condition, the water takes the parabolic profile, and this parabolic profile of water is defined by this equation. This is a part of the question. So Z equals to H plus omega square upon 4G 2R square minus capital R square. Now we need to find out what would be the angular speed of the water of the tank. Then what is the maximum height possible of water? And the third thing is that what would be the pressure at this point A? Okay. So before moving towards the solution of the problem, first thing is that, do you understand the problem statement or not? Now, if you understand the problem statement, let's move towards the solution. Now, the thing is that the first thing is that we need to find out what is the omega, what is the angular speed. Okay, so we can use this equation to find out omega if we know all other parameters. Now, R is fixed, we know capital R. This is fixed. G is acceleration due to gravity, fixed. Capital H is the original height of the water in the tank. This is also fixed. So no issues in that. Now, but we don't know this Z, we don't know this R, and we know that they are interlinked. But we know that for this specific condition, which is shown here in the diagram, the Z is 0 when R is equals to A, right? So when R is equals to, A by 2, because A is 0.2 from here to here, but I'm taking the small radius R from the center. Okay, so when R is equals to A by 2, Z equals to 0 for this specific condition. Okay, so when R is equals to A by 2, Z is equals to 0 here, right? So now I can substitute it here. I can put the value of Z, I can put the value of R. I have all the things unknown except omega. I can find out what is the omega. Okay, so capital R is fixed, small r, I'm putting 0.1, which is 0.2 by 2. And in that case, Z will be 0. So if I substitute the values, I can find that the omega comes out to be 11.84 radian per second. So that means that the container might be rotating at 11.84 radians per second. Okay. Now the question is that what could be the maximum value of Z max? What could be the maximum value Z max? Okay. So Z max can be maximum only in case if R approaches to capital R. If R approaches to capital R. See, your cylinder keeps on rotating. Okay, the time will come when the bottom region is going to expand until all the water is accumulated at the sides. This is the point when small r approaches to capital R. This is the point when the height of the water in the container will become max, because as the water is moving towards the sides, it is climbing up. So when it has actually reached towards the sides to the max, then it has also climbed the maximum top. Okay, so when I say that small r approaches capital R, means the radius have at the point when the radius have approached towards the sides, then the Z will become the maximum as well. So if you place it here, as a small r equals to capital R, then it becomes 2 capital R square minus R square. So it will just become capital R square. Okay, so substitute the values, you're going to get what will be the Z max in the container. Okay. Now the last thing is that at this condition, we need to find what will be the pressure at point A. Okay. Because this is a circular motion, we can apply, and it is considered as a rotational flow. So we can apply Bernoulli's equation. Now, if we apply the Bernoulli's equation, so we have this Bernoulli's equation between, now we are applying it at 2 points, at A and at top. Okay. So when we are applying it between A and top, okay, so at the top, because it is open to atmosphere, so P top will be 0 because it is open to atmosphere. Okay. Now here in this case, at top we have R top, and at bottom we have RA, which is also equals to R top, because this is a equal radius cylinder throughout from top to bottom. Okay, and A is also at the edge of the cylinder. Okay, A is the bottom edge, and here this is the top edge, but the radius would be the same. So these two terms are going to cancel each other. This will cancel this term, right? So now what we are left up with, so we have PA plus gamma. Okay, ZA, we can take this as the start point, bottom. So consider this as 0. So we can find out what we already know, that what will be Z max. Z max will be 1.071, given that ZA is 0. Okay. So if I put ZA 0, so this term also goes. So what are we left up with? PA plus gamma into Z top, and that's it. So just substituting the values, you're going to get what will be the pressure at the bottom edge. Not complete. So that's the solution of this problem. Do you understand the problem statement, figure, and the application of Bernoulli equation within the problem? If there is anything which you do not understand, please feel free to ask. Three vortices. Okay, for the case of ideal fluid flows, how would the flow pattern will be? Now, this is something, a topic that you can go through it yourself. The descriptive, in the descriptive form, it is mentioned here in the slides. Probably, I won't be giving anything from it in the exam, but still it is advisable to go through it. And I'm sure you will go through it. Okay, then we have the pressure coefficient for the case of the gas flows and for the case of the liquid flows. And since actually ideal fluid flow is a separate topic and it has separate applications, so here it is just given as an introduction, so we don't need to go into the details right now here. But it is a part of this course, so it's good if you also go through it. In case of the ideal fluid flows and in case of the real flows, there is a little difference. In real flows, what will happen when there is an obstruction, the fluid will pass through the obstruction, and then you will have a wake region at the bottom, at the back. In the ideal fluid flows, you won't have the wake region. Okay, the fluid remain connected with the body. Go through this description yourself. And there is a boundary layer. Boundary layer association is also there with the ideal flows. That's it. So with this, we are done with chapter number 4. Next thing is to start the next chapter, which is chapter number 5. So lecture week 6 is done. So shall we start the next chapter now? Because we have time, right? We have like 40 minutes with us. अभी फाइनल नहीं हुआ midterm exam. Okay, let's stop the recording.